Hello, welcome back. In this occasion, we're going to talk about the finite element discretization. Let's get right into it. So we left off with the statement of equilibrium stated in the sense of the weak form of the equilibrium equations. That meant that the internal work done during a virtual displacement, if the system is in equilibrium, has to be equal to external work. And with this, we concluded the following. We concluded that the equation looks as follows. Let's fix this a little bit. Looks as follows. Integral over omega delta epsilon transpose sigma dv has to be equal to integral over omega delta u transpose b delta omega plus the term on the boundary. So on the natural boundary conditions, so gamma n, and this is going to be delta u transpose t. Yes. Right, so we started from that. And we have a domain, omega, looks like this. It has its essential boundary, and it has a natural boundary where natural BCs are enforced. Those are tractions, right? And that's the outward normal. This t is equal to sigma dot the outward normal. That's how you get it into the equation, or that's what the meaning it has in the end. Well, we start from this, and now we're going to discretize. So we're going to choose a finite element. Choose a finite element space. So you can talk about finite element space. What does that mean? Okay, let's talk a little bit about this equation. So this equation needs to hold for whatever du you put. Remember that the delta u is a virtual displacement field applied on top of the solution, and it's used to test the solution. It's also called in the finite element literature. If you see books on finite elements, you'll find this, the more mathy books call it the test or trial functions, because you try different of these deformed or virtual displacement configurations, and on trying different ones, this equation must hold for all of them. Okay, so this is valid for whatever delta u you put in there, if the conditions are such that it's equilibrium. So this has u. This u over here gets derived and or differentiated. So delta e is equal d u. Sorry, without the transpose. Yes. Okay, so now that this is valid for all functions, we can't solve this for all the cases. So if it's a general domain, inside those functions there are many functions that could go in there. We just can't do that because it's an infinite space. So we can't find a solution there. Excuse me. We need to restrict the space. So we discretize the solution space. So now what we say is we're not going to admit any solution, any function to be u to be a solution of this problem. We're going to restrict our search into a subset of all possible functions. In this case, the polynomials in our spatial variables. And that's going to restrict and discretize eventually the system. So let's we're going to go off into a triangle very soon, but let's just say there's an element. So now, instead of using our full domain omega, we're going to restrict our analysis to a subdomain, omega e. And you can imagine that this omega e is some little element inside, and that this domain is made with several of these elements. So you can think that the domain might be triangulated something like this. You get the idea. Only triangles. Okay, so let's be complete. It's a really bad triangulation, but this one right here is our omega e, and you can think that this integral omega delta e transpose sigma dv, you can split it up over all e's. So you can split it up and say e equals 0 to, if there are n sub e elements, n sub e elements total. Okay, then this goes to n sub e minus 1. And you put in here the integral over omega e. So for each of these elements, we just split up the domain in this way. Okay, we discretize it like this. And this is what we get. So let's focus on just one of these elements. We discretize the solution space, and let's say that this element connects nodes I, j, and k. And that at each of these nodes, I know ux, at node I, uy, no I, uz if there's a z direction, uxy, uy, j, you got uxk, and uyk. Sorry, the handwriting sucks right now. Anyway, so here's the deal. So you've restricted your domain to one of these triangles, and you're saying I'm only going to know, so these elements are connecting nodes. So these are nodes of the element, and nodes are the points where you know the solution. So you're gonna give up on the idea of knowing the complete solution. You're gonna be satisfied just knowing the solution at some points, called nodes. Okay, so here for each element, this element connects nodes I, j, and k. So node I, node k, node j, right? And we only know displacements there. So if we want to know displacement inside at that point, you have to make an assumption. So we will say that u at any other point is going to be interpolated. It's going to be some interpolation matrix times ue. Okay, so this is an interpolation matrix, this one, and this is the vector of nodal degrees of freedom. Okay, so if we think about it, going back here, u is of shape, it can be 2 by 1 or 3 by 1. Let's just go for 2 by 1 for now. This is in 2D, this is in 3D. UE is the vector that collects all the nodal displacements. So you get ux, I, uy, I, ux, j, uy, j, ux, k, uy, k. So in this case, this is going to be a 6 by 1 vector. Or in 3D, it's going to be a 9 by 1 vector. Okay, depending on the number of nodes. Here I have just 3 nodes, but if there were more nodes in an element, we'll see some of those, we could have more. Therefore, since U is going to be equal, so the solution inside the element is going to be equal to the element's interpolation matrix. Let's stick to the nomenclature, times UE. Then this matrix, the interpolation matrix, has to be of size, for example, 2 by 6 for this to work, or 3 by 6 if we're in 3D. And it's going to look something like this. So UX, UY at a given point. So let's call that point P. Let's give this the displacements at that coordinate are going to be something that has size 2 by 6 multiplying UXI all the way to UIK, the UE vector. And here we get an interpolation function we're going to call N0, E, 0, 0, and 1, E. Sorry, N0, and 0. Let's just correct this. 0, E, and 1, E, and so on, and 1, E, and you'll still get and 2, E, 2, E, 0, 0. Sorry. So NIE is the ith interpolation function. And I takes values 0, 1, 2, depending on the number of nodes. So in this case, 3 nodes. Okay. So U is equal to N, E, UE. Okay, this means all I know are the degrees of freedom at the element nodes. So all I know is how these nodes at the edges displace. So if I'm going to do a virtual displacement of this element, all I need to do is tweak the positions of these degrees of freedom. Okay, they're just 6 values that define my solution, and whatever happens inside gets interpolated from that. So delta U, the virtual displacement field inside this element, is going to be the same interpolation matrix times some other values of the displacement field or the degrees of freedom. So virtual values, whatever you want. Okay, so let's write down, I'm going to restrict the equation, the weak form of the equation. So omega E delta epsilon transpose times sigma d omega is going to be equal to integral omega E delta U transpose B d omega. And I'm going to forget for now about the term with the traction vectors. We're going to go back to that later on this chapter. So now let's use this in here, okay? So what is delta U? So delta U transpose is going to be this guy transpose. So it's going to be NE delta U transpose. It's going to be delta U transpose times NE transpose. Okay, so that's 1, and this one's going to go in here. Let's see this other term. So delta epsilon transpose, what is that? Is going to be delta U. So remember the definition of delta E is du. So this is du, but U we have it defined as NE UE. So in this case delta U, because we're talking about the virtual displacements. Okay, so in this case we're going to get D, and then we're going to have NE delta UE. And we need to transpose all of that. So transpose. And this over here we're going to call B, is formally called the strain displacement matrix. Strain displacement matrix. Okay, so we continue with this. So delta epsilon transpose. If we work everything out, it's going to be delta UE times B transpose, like this. Obviously, we have E equals BU. It follows from a similar idea. And therefore, sigma is E times B times U. Okay, so just multiply this by E, the elasticity matrix. So finally, what we get is the following. We get integral omega, and we have delta UE B transpose E B U delta omega has to be equal to integral over omega E delta U transpose and E transpose B d omega. And right now, these UEs that are listed in there, so this one is also UE transpose, and this came from here, so this is UE. So these ones, you know, they're values at the nodes, so they don't depend on where you are inside the domain. So they're not a function of whatever xy coordinates you have. So that means the UE over there, and the U's can be taken out of the integral. So you get delta UE, this was transposed to omega E, B transpose E, B d omega, and multiply that by UE, has to be equal to delta UE transpose omega E and E transpose B and d omega. And then what we have here is basically what follows. So you want to get rid of this. You want these to cancel out, and the reason you can cancel those out is because you can choose them to be whatever you want. They're virtual, so this equation has to hold for whatever choice of delta UE you have. So you could have the vector 1 0 0 0 0, so 1 followed by 5 zeros, and that would give you one equation, and then you have the next one is going to be 0 1 0 0 0, and that's going to give you another equation. So in the end, what happens is you have a set of 6 equations that you can remove. So you get integral omega E, B, T, E, B, d omega, multiplying UE has to be equal to integral omega E and E transpose B d omega. And we call this over here the element stiffness matrix. This is the element nodal vector, and on the right hand side we have the element equivalent nodal forces. So KE is the element stiffness matrix, and FE is the equivalent nodal force vector, and this is all for element E. So then we can write the stiffness of an element by using these equations, which we will specialize in what comes. Here the value of B and N are going to depend on how exactly you do this interpolation inside, how many nodes you have, and what are the options here. So there are a bunch of options you can have. But the point is, once you decide what your interpolation here is, then you can just go ahead and plug in through the equations, calculate B, compute a stiffness matrix, and then you have this discretized, and you can use this stiffness, the direct stiffness method, to assemble these element by element stiffness equations into a global system, and from that you can get your solution. So next up, we're gonna give actual shapes to this particular interpolation and derive equations for our first finite element. That's all for now.